This is section 5.3, Theorems about parallel lines. It may seem odd that we're going back to studying parallel lines when we did that back in chapter 2, but it makes sense that we're doing it in a chapter about parallelograms because parallelograms are quadrilaterals in which the opposite sides are parallel. So parallel lines have a lot to do with parallelograms. And we're going to see here that we can actually use parallelograms and the theorems that we proved about them in the first two sections of this chapter to prove some things about parallel lines in general. So parallelograms are useful for telling us about parallel lines. So let's say we have a set of parallel lines like this green line and pink line that I've drawn here. I know they're parallel because I've got the arrows pointing towards the right. So what is the distance between a point that's on the green line and the pink line? What's the distance between the green line and the pink line? Well, remember the way we measure the distance from a point to a line is by drawing the perpendicular segment and measuring that. Okay? What if I pick a different point on the green line and I want to know the distance from that point to the pink line? So I draw the perpendicular line. How do these two distances relate to each other? Well, if the two lines are parallel, then that distance should be the same no matter which point I pick on the green line. If I pick any point on the green line, I should have the same distance from there to the pink line. Otherwise, if it's a different distance, then these lines are not going to be perfectly parallel. One of them would be sloped in some way that it would eventually intersect with the other line. That's not allowed if they're parallel lines. They can't intersect. So that distance needs to be the same every time. So if I call this point A, then B, then C, and then D, if I know AB equals 6, then CD equals 6. They have to be the same. Let's state that as a theorem. If two lines are parallel, then all points on one line are what from the other line? Well, what are they? Sorry, I can't hear you. Say it again. Equidistant. Oh, equidistant. Good. If two lines are parallel, then all points on one line are equidistant from the other line. If I pick any 2 points on the top line, it's going to be the same distance from there to the bottom line. So I've drawn two parallel lines, line L and line M. I've labeled point A and B on line L and point C and D on line M, where AC is perpendicular to M and BD is perpendicular to M. If I'm going to prove this theorem, which I am, what do I want to prove? Well, I want to prove that any points on L are equidistant from M. So I've got 2 points on L, A and B. I want to know that they are the same distance from M. So what I want to prove is that the distance from A to C, AC, equals BD, the distance from B to D. We're going to prove this so that you can see how parallelograms are involved. What's the first statement? The given, right. So we copy down the given, and then we want to know what we can see from there. Well, we know L is parallel to M. If I want to find a parallelogram, I've kind of got one drawn there as long as I can show that it's actually a parallelogram. I know the top and the bottom are parallel because L is parallel to M. Do I know that AC and BC are parallel? Well, I know that AC is perpendicular to M and BD is perpendicular to M. And I know that two lines perpendicular to the same line are parallel. So if I've got two lines, AC and BD, perpendicular to the same line, line M, then I know AC must be parallel to BD. It was a theorem we used back in Chapter 2 when we talked about parallel lines. Two lines perpendicular to the same line are parallel. So AC is parallel to BD. So I've got L parallel to M and AC parallel to BD. That means I have got a quadrilateral with opposite sides parallel. Well, if I have a quadrilateral with opposite sides parallel, then that quadrilateral must be a parallelogram. So quadrilateral, which I'll abbreviate QUAD, quadrilateral ABDC is a parallelogram. What tells me that it's a parallelogram? Well, I use the fact that the opposite sides are parallel. What tells me that the opposite sides of a parallelogram are parallel? That is the definition of a parallelogram. Okay, so now I have a parallelogram. How is that useful? Well, I want to prove that AC equals BD. AC and BD are opposite sides of my parallelogram. If we think back to the previous section, we know that opposite sides of a parallelogram are congruent. That will be my reason. Opposite sides of a parallelogram are congruent. So AC is congruent to BD. And of course, the two segments being congruent means their lengths are equal. AC equals BD. And that's just the definition of congruent. If they're congruent, then they're the same size. So we used a parallelogram. We found a parallelogram, this parallelogram, and we used it to prove what we wanted to show. So that's the way all of these proofs in this section will work. So we're not going to prove all of these theorems. I'll prove one more in this video, and we'll get to that one later. Take a look at this theorem. If three parallel lines cut off congruent segments on one transversal, then they cut off congruent segments on every transversal. So if I know that these three lines that I've drawn here are parallel, if I know that this is parallel to this and to this, all three of them are parallel, and I know that AB is congruent to BC. So I've got three parallel lines that cut off congruent segments on one transversal. The red line is my transversal in this case. They cut off congruent segments because AB equals BC. This theorem says they cut off congruent segments on every transversal. So if I draw in any other transversal, any other line that cuts through these parallel lines, that one for instance, according to this theorem, the parallel lines must cut off congruent segments of this transversal. So this segment must be congruent to this segment. So this is G, E, and F. We know we can conclude by this theorem DE is congruent to EF. Those parallel lines must cut off congruent segments on every transversal that we can draw. We won't prove that theorem. Take a look at this theorem. A line that contains the midpoint of one side of a triangle is parallel to another side passes through the midpoint of the third side. A line that contains the midpoint of one side of a triangle and is parallel to another side passes through the midpoint of the third side. So I've got triangle ABC. I've got this other line though, line MN, that cuts through it. It contains the midpoint of AB because M is the midpoint of AB. I see that AM equals MB, so M must be the midpoint. And it's parallel to the other side because I've got those arrows. then this theorem says it must also pass through the midpoint of the third side. So what we would conclude by this theorem is n must be the midpoint of AC. In other words, AN must be congruent to NC, because that line went through the midpoint of AB and was parallel to BC, so it's got to be that it goes to the midpoint of the third side, AC. Now let's say I take almost the same picture, triangle ABC, this line MN that cuts through it. But this time I know not that it's parallel, but that it cuts through the midpoints of both AB and AC. So M is the midpoint of AB, N is the midpoint of AC. So I've got this last theorem here that says the segment that joins the midpoints of two sides of a triangle, and I'm going to be able to say two things about this segment. Segment MN that joins the midpoints of two sides of the triangle, what is its relationship to the third side? It's parallel. Good. It must be parallel to the third side. And how big is it compared to the third side? Well, interestingly, it is exactly half as long as the third side. That is perhaps the most surprising part of these theorems, that MN is going to be half of BC. How do we know for sure it's half? Well, let's prove it. So I've recopied that picture down here, and I'm given that M is the midpoint of AB and N is the midpoint of AC. That's all I need. A segment that joins the midpoints of two sides of a triangle. I know by this theorem then that MN is parallel to BC and MN is half of BC. So let's prove this theorem. I'm not going to prove that MN is parallel to BC. That follows almost directly from the theorem we just looked at above this. That since there's only one line through point M that's parallel to BC, that line has to be MN. So instead, let's just prove number 2. Okay? What do we start with? The givens. M is the midpoint of AB, and N is the midpoint of AC. Reason given. So here's how I'm going to prove this. I'm going to find the midpoint of BC. And let's call that midpoint L. And I'm going to draw, and I'll do this in red, draw NL. So in my proof I'm going to write let L be the midpoint of BC, draw NL. I know that midpoint must exist, so I'm capable of drawing it. And there's really no need to give a reason for that. Then we know by part 1, assume we prove in part 1, that MN is parallel to BC. But if L is the midpoint of BC, then NL is a segment that joins the midpoints of two sides of the triangle, AC and BC. So by part 1, NL must be parallel to AB. I'm just applying part 1 to that new line that I've drawn. NL is parallel to AB. I'll state it with MN is parallel to BC because they're by the same reason. Okay? Now, that means that this quadrilateral MNLB is a parallelogram. Again, by the definition of a parallelogram, since the opposite sides are parallel. So I have a parallelogram. What I want to show ultimately is that MN is half of BC. Well, I know MN, which is one side of my parallelogram, has to be congruent to the opposite side. What's the opposite side? It's BL. So MN is congruent to BL because opposite sides of a parallelogram are congruent. But BL is half of BC because L is the midpoint of BC. How do I know it's half? Is that the definition of a midpoint? No. If I see half, it's the midpoint theorem. Good. So BL equals half of BC. So this is an excellent application of the midpoint theorem, which we don't normally use. We usually use the definition of a midpoint to say that the two segments are congruent. So if I want to say it's half, it's the midpoint theorem. So that means MN must be half of BC because MN is equal to BL. MN is congruent to BL, so it's equal to it. So this is just the substitution property. We cannot call this transitive. In this case, it has to be substitution because we're plugging it into an equation. We don't have a chain of things that will make it transitive. One quick example of this. I've got this triangle, DEF. I've drawn the midpoint of DE, which is P, the midpoint of EF, which is Q, and the midpoint of DF, which is R. So P, Q, and R are the midpoints of the sides of triangle DEF. What kind of triangle, or sorry, what kind of figure is DPQR? Well, by the theorems we've just shown and proven, if P is the midpoint of DE, then PQ cuts through the midpoints of DE and EF, so PQ must be parallel to DR. And similarly, since R and Q are the midpoints of those two sides, RQ must be parallel to DP. So DPQR is a parallelogram. And what is the perimeter of DPQR? Well, I know DE is 12, EF is 10, and DF is 8. Perimeter, remember, is the distance all the way around the shape. So how big is DP? Well, if P is the midpoint of DE, then DP is half of DE. So DP is 6. So we've got at least 6. How big is DR? Well, R is the midpoint of DF, so DR is half of DF. DF is 8, so DR is 4. So we've got 6 plus 4. How big is RQ? Well, because I have a parallelogram, and because I know RQ is half of DE, by the theorem I just proved, then RQ has to be half of 12, which makes RQ 6. How big is PQ? Well, PQ must be half of DF, by the theorem I just proved. DF is 8, PQ is half of it, PQ is 4 then. So I've got 6 plus 4 plus 6 plus 4, which is 20. You're going to follow a very similar process, and that last theorem I just proved, to complete your immediate practice problems. I've got that triangle, then I've drawn the midpoints of the triangle, H, A, and E, and I've drawn the segments that connect those midpoints. So if H, A, and E are the midpoints of the sides of triangle SRV, fill in the chart below. So each row of the chart, each row of the table is a separate problem. So in problem number 1, you know VS is 12, SR is 14, and VR is 18. Use those to find HA, AE, and HE, using the last theorem that we stated in the notes. Then in problem number 2, you know SR is 16, VR is 22, and AE is 10. Use those to show and find what VS is, HA, and HE are, using the last theorem that I just proved. That is the end of section 5.3.